Today, we will explore the fundamental physical processes underlying the electrical breakdown of a gas, which marks the transition from an insulating medium to a conducting plasma. This phenomenon is governed by a cascade of microscopic events, the understanding of which was pioneered by John Seely Townsend. Let us begin by considering the initial conditions. We have a gaseous medium, contained between two planar electrodes separated by a distance *d*, with an applied voltage V. Under normal conditions, the gas is an excellent insulator. However, a minimal population of free electrons is always present due to natural background radiation or field emission. When an electric field E is applied, these initial electrons are accelerated towards the anode. The central mechanism of the initial breakdown phase is the electron avalanche. As a free electron undergoes acceleration in the electric field, it gains kinetic energy. Between collisions with neutral gas atoms, its energy increases. When an electron's kinetic energy exceeds ionization potential of the gas atom, a collision can result in ionization. This process liberates a secondary electron, leaving behind a positive ion. Consequently, one incident electron produces two electrons post-collision. Both these electrons subsequently accelerate and can, in turn, initiate further ionization events. This results in a multiplicative cascade, or an electron avalanche, where the number of electrons grows exponentially as a function of distance through the gas. The quantitative description of this process is given by the Townsend's first ionization coefficient, denoted by alpha. This coefficient is defined as the number of electron-ion pairs produced per unit length by a single electron drifting in the electric field direction. The electron current at a specific position from the cathode thus follows the relation shown here. The equation yields an exponential solution for the current growth. However, this avalanche process alone is insufficient to sustain a continuous discharge, as the primary electrons are ultimately collected by the anode. For a self-sustaining discharge to be established, a mechanism for regenerating electrons at the cathode is essential. This is achieved through secondary processes. The positive ions generated in the avalanche drift towards the cathode due to the electric field. Upon impacting the cathode surface, these ions can liberate new electrons through kinetic emission or potential energy transfer. This phenomenon is termed secondary electron emission. The efficiency of this process is quantified by the Townsend's secondary ionization coefficient, denoted by gamma. It is defined as the number of secondary electrons emitted from the cathode per incident positive ion. Other processes, such as photoemission from photons emitted by excited gas atoms, also contribute to the secondary electron yield, but ion-induced emission is typically the dominant mechanism for gamma. The condition for a self-sustaining discharge, known as the Townsend breakdown criterion, is derived by balancing the electron production at the cathode with the electron loss at the anode. The criterion states that for a discharge to become self-sustaining, the production of secondary electrons must be sufficient to replace the initiating primary electron. This leads to the fundamental equation defining the efficiency of electrons' regeneration. When this inequality is satisfied, the discharge can persist independently of the original seed electrons, and the gas is said to have undergone electrical breakdown. Finally, we must address the practical parameters governing breakdown. It is empirically and theoretically established that the breakdown voltage is not an independent function of pressure and gap distance but rather a function of their product. This relationship is graphically represented by the Paschen's curve. The curve exhibits a characteristic minimum. The physical explanation for this shape is as follows. At low PD values, high vacuum or very small gaps, the mean free path of electrons is large. Consequently, electrons traverse the gap with a low probability of initiating ionizing collisions, necessitating a higher voltage to achieve the necessary gain. Conversely, at high P times D values, high pressure or large gaps, the mean free path is short. Electrons undergo frequent collisions but cannot gain sufficient energy between collisions to reach the ionization threshold, again requiring a higher voltage for breakdown. The minimum of the Paschen curve therefore represents the most efficient operating point for breakdown, where the balance between collision frequency and energy gain is optimal. In conclusion, the transition from a gas to a plasma is a precisely quantifiable process. It is initiated by an electron avalanche characterized by the primary coefficient alpha, sustained by secondary emission at the cathode quantified by gamma, and governed overall by the Townsend criterion. The practical threshold for this transition is elegantly captured by Paschen's law, which remains a critical design principle in everything from plasma processing reactors to high-voltage insulation systems.